Hello, my name is Manuel Rivera. I'm an assistant professor in the Department of Mathematics at Purdue University. I did my PhD at the CUNY Graduate Center under the supervision of Dennis Sullivan. My field of research is called algebraic topology. And today I'm going to talk about the Borsuk-Ulam theorem, which is a theorem it was proven in mid 20th century. And the proof used ideas from my field of research, algebraic topology. But the theorem itself really has applications all over mathematics. And I think of it as a theorem that it even has philosophical applications. Um, and I will share a little bit about this at the end of my talk. I hope you enjoy it. So the Borsuk-Ulam theorem. So let me start with two interesting facts about our physical reality. So first, there is always a pair of antipodal points, namely opposite points, on the equator of the Earth with the same temperature. So the equator of the Earth is a particular circle going around the surface of the Earth. And this fact that I'm telling you, which we will actually prove mathematically, says that there's always two opposite points. Antipodal means opposite, that have the same temperature at any given moment. Moreover, there is always a pair of antipodal points on the surface of the Earth with the same temperature and the same humidity. This is kind of a funny, interesting, curious fact if you think about it. Why should that be the case? Well, these are consequences of two basic principles of our physical reality. First, that the surface of the Earth is approximately a sphere, and that the examples of the quantities I gave here, such as temperature and humidity, vary continuously as you move along this Earth's surface. So let's try to make this into a precise mathematical statement. And then let me give you an idea of why these statements are true. Namely, let me give you a proof. So before I give a precise mathematical statement, let me say precisely what I mean by antipodal points. So for example, a circle, you can think of the circle of radius 1 as the pair of points in the plane xy, such that x squared plus y squared equals 1. And a pair of antipodal points is a point in the circle x0, y0, and its antipodal pair, it's the negative of that point, namely minus x0 minus y0. So you can think of the antipodal point as the reflection of that point along the origin. Namely, 2 points are antipodal, 2 points in the circle are antipodal if you can join them by a straight line segment that goes through the origin. So that characterizes antipodal points. So you have the same idea on the two-dimensional sphere, which lives in space, in the XYZ Euclidean space. So you can define the two-dimensional sphere as the set of all triples of numbers, x, y, z, or all points in space, such that their coordinates satisfy the following equation: x squared plus y squared plus z squared equals 1. This gives you the sphere of radius 1 centered at the point 0, 0, 0, the origin of space. And now you can say two points are antipodal. Again, if you can join them by a segment, a straight line segment that goes through the origin. Or in other words, 2 points are antipodal if their coordinates are differ by a negative sign, right? So, and we say that minus x is the antipodal of x. So now let's try to make the facts I just said into a precise mathematical statement. And this is what's known as the Borsuk-Ulam theorem. So first, for a circle, for any continuous function, real valued continuous function f defined on the circle, I'm going to call the circle S1, there exists some point in the circle such that f sends the antipodal of that point to the same value associated to the point x. So both x and minus x have the same value under f. So this makes precise what I said about having two antipodal points on the equator. The equator is a circle on the surface of the Earth. 2 points in the equator, which are antipodal, having the same temperature. So this theorem says that these always exist. It doesn't matter how your function is defined. You're just requiring that your function in the circle is a real valued continuous function, such as temperature, for example. For every point in the circle, I assign a number. You can think of that as the temperature. And I'm assuming this value is varying continuously as I move along the circle. Just assuming this, we will prove that you can always find two antipodal points that have the same value, same temperature. So let me make a precise statement for what I said about temperature and humidity on the surface of the Earth. So this is our second theorem. So for any continuous function on the sphere, I'm denoting the sphere by S2. This is the sphere living in space. There exists some pair of antipodal points in the sphere that have the same value under this continuous function. But note that this continuous function, the range of this continuous function is the plane. Namely, I'm associating to every point in the sphere a pair of real numbers. And I'm assuming that these vary continuously as I move around the surface of the sphere. So let me say that again. We have a function on the sphere which associates to every point in the sphere two numbers, such as temperature and humidity. And I'm assuming these vary continuously. Under these assumptions, you can always find a point in the sphere such that f will send the antipodal of that point and that point to the same value, to the same pair of numbers. In other words, for example, there's always a pair of antipodal points in the surface of the Earth that have the same temperature and the same humidity, or the same temperature and the same pressure, for example. I'm just requiring these quantities to vary continuously as I move along the surface of the Earth. And I'm also requiring that these are two quantities. And more generally, the Borsuk-Ulam theorem is the same statement, but for the n-dimensional sphere. So if you have a function, a continuous function, from the n-dimensional sphere to the n-dimensional Euclidean space, then there's always a point which gets sent to the same, there's always a pair of antipodal points which get sent to the same value under F. This is called the Borsuk-Ulam theorem. It holds in this level of generality. We will concentrate on the first two statements today. I will give a precise proof for these two. For the first theorem, I will use the intermediate value theorem that you have probably seen in your calculus lessons. And for the second theorem, I will give a picture proof. I will try to convince you with a picture. Yeah, I will not prove the general theorem, but let me say that this general theorem uses ideas from my field of research, which is called algebraic topology. I might say a little bit more about this soon. So the proof of theorem 1. So any continuous function on the circle has a pair of antipodal points that get sent to the same value. Any continuous real valued function. Let me try to explain why this is true. And as I said, this is a consequence of the intermediate value theorem. So suppose f is a continuous real valued function, and we're going to consider the new continuous function defined as follows. For every x, I define g to be f of x minus f applied to minus x. So for example, if g of x equals 0 for all x, then this would imply that f of x equals f of minus x by the definition of g, right? In particular, this will imply that all pairs of antipodal points will get sent to the same value, and we would be done. So otherwise, if this is not true, if g of x is not equal to 0 for all x, there will be some point y in the circle such that g of y is greater than 0 or g of y is less than 0, right? So let's assume there is some y with g of y greater than 0. I'm assuming this without loss of generality. The second possibility will lead to a similar argument. So if g of y is greater than 0 for some y, then using the fact that g of minus y equals f of minus y minus f of y, I'm just plugging in minus y in the definition of g up here. I get that g of minus y equals minus g of y. In other words, this new function g that I defined is an odd function. So since g of y I was assuming is greater than 0, this means that g of minus y will be a negative number. Therefore, g of minus y is less than 0. So we have a continuous function g, and we have found that g at some point y is greater than 0, and g at another point minus y is smaller than 0. So by the intermediate value theorem, this means that since g is a continuous function, for some x, for some point x, g will have to be 0 at x. In other words, if g has a positive value at some y, and g also has a negative value, in this case at minus y, then at some point in between, g will cross 0. G will attain the value 0. But what does this mean? remember we defined the g of x to be f of x minus f of minus x. So this would mean that this quantity, this difference, is 0. But that means that f of x equals f of minus x, which means that f sends a pair of antipodal points to the same value. So it's a consequence of the intermediate value theorem. And of course, the fact that we are considering a function defined on a circle. Now let me give you a picture proof of Theorem 2, namely the Borsuk-Ulam theorem on the sphere. So let me remind you what was Theorem 2. Theorem 2 was the statement that any continuous function defined on the sphere with values on the plane sends some x to the same value at its antipodal point. So for any continuous function, you can always find a point x such that f of minus x equals f of x. And remember that f takes values in pairs of numbers, pairs of real numbers, points in the plane. So let me try to guide you through this picture. So suppose we are given a continuous function f defined on the sphere with the values on the plane. We're going to do the same trick. So I'm denoting here bold x to be the points in the sphere. I'm using this bold x notation because a point in the sphere is really a vector, right? It's a point in space whose squares of coordinates equal to, in this case, I'm assuming 1, radius 1. So we do the same trick. We cook up this new function g. So g of x will be defined to be f of x minus f evaluated on the negative of x. And as before, we want to show that g of x equals 0 for some point x in the sphere. Because if g of x equals 0, by the definition of g, that means that f sends x and the antipodal of x to the same value in the plane. So how do we do this? So let's look at this picture. So first consider any two antipodal points in the sphere. I have denoted them here by x and minus x, and they are colored green. So consider any two antipodal points in the sphere. Then, since g of minus x equals minus g of x, as you can check from the definition of g, that means that the image of x along g in the plane, namely this point here, g of x, if you consider that point and you consider the point g of minus x, they will be opposite points in the plane. Namely, g of minus x equals minus g of x. So it means that you reflect along the origin and you come back to the point g of x. That's part of the odd symmetry of the function g. You've probably learned about even and odd functions in your calculus classes. So it's the same principle. G is an odd function, namely g of minus x equals minus g of x. So G has certain symmetry, certain rotational symmetry, and that's what I'm using here, right? And now I can consider here, so these x and minus x are two antipodal points. I can consider the circle going through them, right? There's always a circle, an equator going through any two antipodal points. And now I can divide that circle into two half circles, which I've colored here red. This is the first half circle. And then blue, the second half circle. Now I'm going to look at the image of those half circles under G. So the image of the red path, let's say it's this red path in the plane here. That's a picture for the image, but then that determines the image of the blue path, the image of the other half of the equator. Why is that? So that again uses the symmetry of G. G has rotational symmetry because G is an odd function. Namely, if I rotate this path, this red path, 180 degrees, I get the blue path. So these two paths are symmetrical along the origin. Okay, so if it happens that one of these paths goes through the origin in the plane, then I'm done because I have found a point in the sphere that gets sent to the origin, gets sent to 0, 0. And that's what I wanted to show, that there's a point X in the sphere that gets sent to 0 under G. Let me say that when I write 0, I mean the point 0, 0 in the plane. I'm using that notation. I'm just denoting by 0 the point 0, 0, the origin of the plane. Okay. So if it happens that one of these paths go through the origin, I'm done. So let's assume they don't. So the picture is really something looking like what I have drawn here. Let's assume none of these two paths go to the origin. So now I'm going to look at this equator on the sphere, and I'm going to do the following. I'm going to consider the family of circles. They're pictured here by gray, or I should say a family of circles that describe a deformation of your circle, a continuous deformation of your circle, of your equator, of the equator onto the North Pole. So I can always find a family of circles that describe a continuous deformation of this equator circle onto the North Pole. So it's like a movie that you're getting, you play this movie, you start with the equator, and your circles are getting smaller and smaller until they become the North Pole, right? And all of these circles are in the surface of your sphere. So consider that family. You can always find that in the sphere, right? You can always deform an equator to the North Pole. So now look at the image of all of those circles in your family under your function G. I have drawn here these gray lines to describe those images. And I have also denoted, so P is the North Pole, and I have denoted the image of the North Pole here by G of P. It's the purple dot here. So let's suppose that that's the image of the North Pole. So this family of loops which correspond to this family of gray circles on the sphere are becoming closer and closer to the point GP until they actually become the point GP. It's a deformation of this loop in the plane into a point GP in the plane. But at some point in this continuous deformation, since this loop contains the origin, at some point it will go through there will be a loop that intersects the origin. What does that mean? That means that there's a loop here, one loop in this family, in this continuous deformation, that gets sent under G to that loop that intersects the origin. So that point, that purple point here, pink point, it's a pink point, it's the origin, that point comes from a point in one of the loops in your circle, in your sphere, which, for example, I've colored it here purple, say. So what does that mean? That there's a point, there has to be a point in the sphere that gets sent to the origin in the plane after applying G. So that means that there's a pink point here in the sphere, such that if I apply G to that pink point, you get 0, 0, which is what we wanted to show. And notice this follows from continuity again. There's a continuous deformation of this equator into the North Pole, and that family of circles you get is continuous. So that means that the image of the loops in the plane at some point will have to intersect the origin, which is what you wanted. See? Let me say again that if you have a point if you have a point X such that G of X equals 0, by the definition of G, that means that F of X and F of minus X have the same value in the plane in R2. And you're done. So that's cute, right? That's a nice argument. And the general theorem, which says that for any continuous function in the n-sphere with values in the n-dimensional Euclidean space, there's a point x in the n-sphere such that f of minus x equals f of x, can be proven by using ideas from algebraic topology. So there are several proofs. I know of a combinatorial proof, and I also know of a proof that uses ideas of algebraic topology, which is my field of research. Algebraic topology is a field of mathematics in which we associate algebraic objects such as vector spaces, groups, rings, or fields to geometric spaces and geometric shapes in a way that if you deform your geometric shape, your algebraic object will remain invariant in a specific way, let's say. So that's the main idea of algebraic topology. And you can prove this more general theorem using this kind of ideas. It's very neat. I should say something about the history. So Borsuk and Ulam were two Polish mathematicians that lived around the same time in the 20th century. Borsuk was influential in topology. He has other important theorems in algebraic topology, but Ulam was all over the place. He was very influential in nuclear physics and computer science, in applied mathematics, in biology, and in other fields. I invite you to look up a little bit about the history um, of Ulam. Um, you can search online and you will get lots of information, historical information about him. He was very influential and very well known. And actually, this statement, this Borsuk-Ulam theorem, does have applications outside topology and outside mathematics as well. In fact, there are many papers and books written about this single theorem because of its multiple application, consequences, and even generalizations inside topology itself as well. So as an application, let me discuss the so-called ham sandwich theorem. So what is this about? That's a funny name. So the theorem says the following. If you have three solids, B1, B2, and H in space, so you think of these solids, B1 and B2, as two pieces of bread, and you think of H as a chunk of ham. That's why it's called the ham sandwich theorem. The theorem says that there exists a plane, which you can think as your knife, which cuts the three solids with a single straight cut in a way that divides the three solids, your sandwich, by half. That divides the volume of these three solids by half. So you have two pieces in the end. Each of them has half of the volume of B1, half of the volume of B2, and half of the volume of H. That's a cool theorem because it doesn't matter where your solids are. They can be anywhere in space. And you can always find a plane that goes through the three of them. And moreover, it cuts the three of them in half. And what's more amazing is that this theorem follows from the Borsuk-Ulam theorem. So let me try to explain that. It uses the Borsuk-Ulam theorem for the sphere, the version for the sphere that we've seen. So there's a picture. So this is B1, the first piece of bread. This is B2 here, your second piece of bread. And this is H, which you think of as the ham in your sandwich. And this is the plane, which you think of as a knife. And the theorem says that you can always find a plane, it doesn't matter where your three solids are, that divides B1 into two pieces of equal volume, divides H into two pieces of equal volume, and divides B2, your second piece of bread, into two pieces of equal volume. So I want to explain how this statement follows from the Borsuk-Ulam theorem for the sphere. So first of all, let me say the following. Suppose you're looking at the space. So these three solids, B1, H, and B2 are in your space. And suppose the origin of your space is down here. So I've located the origin of space. You just choose, or you choose an origin, a point that serves as the origin, right? And you can consider a sphere, let's say of radius 1, centered at your origin, okay? Now, any point x in the sphere determines a vector that starts at the origin and has its endpoint at the point x, right? Any point in your sphere determines a vector. like this one in the picture. And any vector determines a family of planes. In what sense? Given a vector based at the origin of space, you can consider the plane which is perpendicular to that vector. Like that. Suppose this blue pencil is your vector based at the origin and whose tip is a point in the sphere of radius 1, say. There's always a plane perpendicular to that vector. So that vector determines a plane. And now you can sweep this plane all over space to obtain other parallel planes, which are still perpendicular to your vector, right? You can sweep it. So that's a family of planes I mean when I say that a vector, a point in the sphere determines a plane, determines a family of planes, I'm sorry. So any point in the sphere determines a family of planes perpendicular to the vector having that point as its tip and based at the origin. Okay? So I want to use this family of planes in the proof of this ham sandwich theorem. So bear with me. So as I said, every point in your sphere determines a family of planes perpendicular to the vector x just by sweeping the plane that goes through the origin, which is perpendicular to your vector. And one of these planes in your family cuts the ham, the solid H, in half. Again, this follows by continuity, right? You can just keep sweeping your plane until, suppose this is your piece of ham, and that's your plane in the going through the origin. You can just sweep it until it cuts your ham by half. You can always do that, right? By continuity. You're only looking at the ham. You're not thinking about the pieces of bread. So given any point x in the sphere, you can always find this plane, which we call P of x. So P of x cuts the ham by half. It might or might not cut the other pieces of bread by half. It might not even intersect the other pieces of bread. That's fine. I'm just looking at the chunk of ham. So this plane P of x is perpendicular to the vector associated to x and cuts the chunk of ham by half. So now we will define a function f on the sphere S2 with values on the plane. And this function will be continuous. So the function is defined as follows. For every point x in the sphere, you look at the plane P of x, and the first number in your output will be the volume of the first piece of bread of B1, which lies on the positive side of your plane. So note that each plane has a positive side and the negative side. That's because each plane is determined by a vector, and a vector has a direction. So I just denote the positive side to be the side into which the vector points. So if my vector is the blue pencil here, this side is the positive side, and this side I will call the negative side. Okay, so let's go again. So P of x is a plane which cuts the ham by half. So the first coordinate of my function will be how much volume of the first piece of bread is on this positive side, right? So your piece of bread might be up here, and this, let's say this is your plane. So as you can see, the plane cuts the piece of bread. So half of it is on the some portion of it is on the positive side, and another portion of it, it's on the negative side. Okay. It might be that your whole piece of bread lies in the positive side, and there's nothing on the negative side. Okay. Why not? So that's going to be the first coordinate of your function. Second coordinate of the function is the same for the second piece of bread. So the second coordinate of your function is the volume of the second piece of bread, which lies on the positive side of the plane px, which cuts the ham by half. Okay. So I've defined a function. And you can argue, it's intuitively clear, that this function is continuous. As you vary your point in the sphere, your plane px will vary continuously, and therefore these two quantities will vary continuously. So since f is continuous by Borsuk-Ulam, there is a point in your sphere, let's call that point y, such that f of y equals f of the antipodal of y. So there's a pair of antipodal points that get mapped to the same pair of points in the plane. So the same point in the plane, sorry. The same pair of numbers. However, both the planes py and p minus y are the same, right? If this is the plane, and if you have the blue vector, which determines a perpendicular plane, the opposite of this blue vector, or the vector determined by the antipodal point, will also be perpendicular to your plane, but will point in the opposite direction. So both y and minus y determine the same perpendicular plane. What changes is just that the planes have now different positive sides, right? The positive side of one becomes the negative side of the other. So what does this mean? So this means that, let's look at the first coordinate of your function f on this point y. So that's the volume of B1, the first piece of bread that lies on the positive side of PY. But since that's equal to f of minus y, that first coordinate of your function f equals the volume of B1, which lies on the positive side of minus y. But as we said, the positive side of p of minus y is the negative side of py. So what is this plane doing? This plane py is splitting b1 in half. So this plane has half of the volume of b1 on one side and half of the volume of b1 on the other side. So it's splitting the first piece of bread by half. And the same argument applied to the second coordinate of this function f shows that this plane py splits the second piece of bread, b2, in half. And voila, this plane defines the cut, because by definition of these planes, py cuts the ham in half. So that's kind of amazing that this fact, this Borsuk-Ulam theorem, which we illustrate as saying that two antipodal points on the surface of the Earth have the same temperature and same humidity gives us this ham sandwich theorem. I find that mind-blowing. A priori, these two principles are not connected at all, right? And then you can see that they're intimately connected. They boil to the same mathematical statement. That's cool. In another application, I call it the political spectrum principle. So this is part of a small project I've been working on with a colleague. His name is Jose Samper. He is at Max Planck Institute in Germany. So we were playing around with this one day, and we realized that the Borsuk-Ulam has deep philosophical implications, actually, which can also be explored from the perspective of discrete mathematics, of computer science, of data analysis, and so on. So this is the idea that the Borsuk-Ulam theorem tells us that, in principle, locating a person in a one-dimensional left and right spectrum based on a series of more than one political ideas and position is not a good idea. So it's not a good idea. Just suppose you have a person and you know something about a few of his ideological positions. It's never a good idea to say, oh, this person is left wing or right wing based on this. And that's a very cool principle and interesting and relevant to our times, you know, like projecting a person to a left and right spectrum. It's never a good idea, even for a fair notion of projection. So let's explore this idea a little bit more. So suppose you have n variables, x1 and up to xn. And let's say each of these takes a value between 0 and 1. So we want to think of each variable as some kind of like ideological position on some political issue, right? For example, 0 means that it's the leftmost position, which we call like liberal or something, and 1 is the most rightmost or conservative value you can take in this on an issue or position, right? So let's assume the space of all possible positions is then a cube. So I mean, if I assume that each variable of these x1 up to xn can take a value between 0 and 1, then the space of all possible positions is the n-dimensional cube, right? So if I have a person, I can, based on these n principles, I can locate it on the cube, right? And we've seen these in social media, right? There are these like X and Y planes that say one axis denotes like your position on social issues, and the other y-axis say denotes your position on economic issues. So where in the plane are you located, and how do we pair you with a candidate or things like that based on your location in the plane, right? We've seen this these kind of this kind of framework before. So the mathematical theorem is the following: given any continuous map from the n-dimensional cube into an interval, you can always find 2 points in your cube which are pretty far apart. And we have an estimate which is square root of n minus 1, the distance between these 2 points, that gets sent to the same value in your interval. And the proof uses Borsuk-Ulam theorem, and the fact that inside the cube of all possible positions, you can always find a circle, quote unquote, because it's not a perfect circle. It's the image of a circle under what we call a homeomorphism, whose all pair of antipodal points are at distance at least square root of n minus 1. So by Borsuk-Ulam theorem, if you restrict your function f to this loop, which you can think of as a circle, inside your cube, then f will send 2 antipodal points to the same value. And these 2 antipodal points will be of distance at least square root of n minus 1. So what does this have to do with this discussion of the political spectrum? So I'm thinking of f as some way, some fair way. That the continuity part tells you that it's a sensible way of projecting a person based on n values to a one-dimensional spectrum, right? So if you have someone which has, you can plot in this cube based on his position on the fixed n political issues, let's say, and you can plot his values on this cube. This f, this continuous map, would project to the interval. So it would be a way of saying, oh, this person, based on those principles, is a left-wing person or right-wing person, because it lies at the left of the midpoint of the interval, and that makes him a right-wing person. No, this can be very bad. Why? Because you can find 2 people who are very opposite in their views, which get mapped to the same value in your projection. See? So, of course, this is done at the level of the space of all possible positions. It might be that when you plot your data, the shape that your data forms, it's not a cube, right? Which is probably true. Reality will not be a cube, like your data will not be spread evenly on a cube. However, I think this is still an important principle, a philosophical principle, that it's not good to project. You will forget too much information. And not even that, it means that you can always find very far apart points that get mapped to the same point after your projection map, right? Oh, and moreover, note that as n goes to infinity, because of this bound here, square root of n minus 1, projecting to a one-dimensional spectrum becomes a worse idea. As you keep adding more positions or more political issues, projecting down to a one-dimensional spectrum is even a worse idea. You can find people with bigger distance inside this bigger cube, which get mapped to the same value under this projection. So we can try to modify this setup so that it is closer to reality. As I said, the space of positions might not actually be a cube, right? The space of the data might not actually be a cube. So this leads to interesting geometric questions if you start playing around with different shapes of possible data. And you can start estimating the minimum distance of antipodal points, whatever that means in this new shape, that gets sent to the same value, right? And this leads to questions in discrete geometry and computer science, which are interesting, and even in geometry. So I think this is the end of my talk regarding the Borsuk-Ulam theorem. I hope you got an idea of first the proofs um, in the cases of dimension 1 and dimension 2. There are two essential ingredients: continuity and the spherical nature of your shape. And I hope you got an idea of the different applications that this principle can have, this Borsuk-Ulam theorem can have. We saw the ham sandwich theorem. We saw this political spectrum principle, as I call it. So it's a really important principle, not only inside mathematics, not only inside geometry and topology, but it's all over the place, actually. So I hope you enjoyed this talk. Now let me say a little bit more about me, about my math career, about grad school, and so on. So what do you love most about mathematics? Actually, I think this talk captures what I love about mathematics. I think in this talk we can see that there's this statement which is aesthetically pleasing. It's beautiful, right? There's some beauty to it. And we explained the reason behind this statement, and the proof itself is also aesthetically pleasing. It has beauty in it. It has creativity. But on the other hand, this principle can also be applied in other fields, can also be applied to derive other principles, can be applied to understand the physical reality. So that's what I like about mathematics. It's a field in which, first of all, you're actually able to understand something concrete based on some axioms. Understanding ideas is always good, right? There's very little we have understanding of very few things in this world, right? Like real understanding. And I think in mathematics you can actually understand something, and that can be related to physical reality. It usually is, right? And on the other hand, as I was saying, there's also an artistic aspect to it. There's beauty, there's aesthetics, and I like this interplay. That's what I love most about mathematics. The interplay about the beauty, the aesthetics, and truth, on getting to the bottom of things based on a few principles or axioms. Yeah. What was your favorite math topic as an undergraduate? So I took this mathematical logic class that I really liked. I learned about first order logic, set theory, and so on. I also took an intro to topology class, of course, and I liked that a lot. There's this idea, which is the basic idea of algebraic topology, in which you associate an algebraic object to a geometric object, and I love that idea. when I saw it for the first time. The fact that you can use mathematics to relate two different fields of mathematics. That was very interesting, beautiful. So would say my favorite math topics were topology and logic, actually. How did you prepare for grad school? Um, that's a good question. I'm not sure I really knew what I was getting into uh, right before grad school. So let's say, so of course, as an undergrad, I took math courses, um, and those, yeah, those math courses which really interested me, as for example, I took a topology course. I I established a closer contact with the professor of that course, and I asked him for about what's next about after this topology course. Where can I learn more? And he gave me good advice. He suggested some further reading. That's how I got into algebraic topology, and he also told me about universities that had good algebraic topology PhD programs. So I think if you're an undergrad and you're starting to think about grad school, you should seek advice from um, someone who taught you something interesting in undergraduate mathematics, and that person will give you better advice in how to prepare for grad school, um, given um, your knowledge and your level and all of that, and your performance, of course. What was the most challenging part of grad school and how did you handle it? Oh, there were many challenging aspects. So, first, there's a time constraint. Um, you have like from 5 to 6 years or something. And in this period, you have to prove your own theorems. That was very challenging. Like, um, I was not sure if I was going to be able to prove my own theorems in a restricted time frame. Why would I, right? So that was the most challenging part, I would say, the time constraint to produce something original and creative. And how did you handle it? So I think I handled it by focusing on a very particular aspect of the problem I was working on. Right, when you're in grad school, you're bombarded with like knowledge, new ideas. There's seminars. There's people coming in to visit and giving talks and using fancy words and big words and talking about interesting things. And this can be distracting. Um, and you have to be able to manage your time wisely because you have a time constraint. So I think I handled this just by focusing on a very particular narrow aspect of the problem I was assigned to work on. Okay. And kind of at the end of grad school, I decided to block a little bit of the other distractions like conferences and other seminars and things like that. And that worked for me in particular. Do you have any general advice for students considering pursuing the doctorate? Yes, I have advice. I think if you're thinking of pursuing a PhD, you have to make sure you have passion and you love what you're going to study, be that mathematics or any other subject. PhD is at least 5 years of your life. in which you're fully dedicated to this. And in order to succeed and produce something, you need passion and love for what you're doing. Um, you kind of have to fall in love with the subject. So make sure um, you have that for the subject you're considering studying. Um, that would be the main advice I would give to students pursuing a doctorate. Okay, thank you. I hope you enjoyed this talk. Um, Please let me know if you have any questions about anything, about mathematics, about um, graduate school in mathematics. Um, my email is the following. Let me write it here. It's Manuel R at purdue.edu. This is my email. MANUELR at purdue.edu. You can email me. We can set up a time to talk if you're interested, and we can talk about anything. I can suggest further reading if you're interested in what you heard about the Borsuk-Ulam theorem, or I can give you further advice about graduate school in mathematics. So that's all. Bye.